Okay, so let's look at our first potential energy, and it's going to be gravitational potential energy. So the potential energy that is associated with gravitational force is called gravitational potential energy. Okay, it's going to be given, all potential energies are given the symbol U. Okay, so U sub G would be the symbol for gravitational potential energy. So basically the way to think about it is the work done by or against gravity. Okay, and the formula, work equals negative mg delta y. Okay, now you could use this integral equation up here, this u equals negative fx dx to get this equation, but you don't necessarily have to. If you want to see that just real quick, so u equals negative mg delta y or dy, right? And if we just say from like y0 to y, it gives us our delta y. If it's constant, it's just going to get the linear. So it becomes negative mg of y minus y0, which leads right to that equation. Okay. Now, what happens with the negative sign? So negative work, remember, takes away from the kinetic energy. Okay, and what happens when you go up? Okay, and then positive work it'll add or gives kinetic energy, and that's going to happen as you go down. So if I have something here and I lift it up to a height, right, I'm taking away from its potential energy, because remember, force always wants to go to lower potential energy. But then if it falls, right, it's doing positive work, again, because of the way the forces act. Remember, gravity acts down. If I'm lifting against it, right, my angle would be 180. But if I'm letting it fall, my angle would be 0. Now, if the only force acting on the object is gravity, again, remember, delta K equals negative delta U, okay? And this is conservation of energy, okay? So the change in kinetic energy is equal to the negative change in potential energy. Now, if you set the initial position equal to 0, then the formula just simply becomes U equals, or U sub G equals mgh, or you can call it mgy, right? Whichever one you want to use. Okay, most of the time you'll see it as h, but sometimes you will see it written as y. Okay. Now here's a couple of quick examples. So the lowest point in Death Valley is 85 meters below sea level. The summit of nearby Mount Whitney has an elevation of 4,420 feet. What is the change in potential energy when an energetic 65-kilogram hiker makes it from the floor of Death Valley to the top of Mount Whitney? Okay, and so it's something like, here's kind of our physical picture. This is my h equals 0 point, which makes this Death Valley negative 85 meters, right? And so this is sea level, right? Okay, and it makes this 4420, right? And so if I want to calculate the change in potential energy, I'm just going to do mg delta y. So it's going to be 65 times 10 times final, which is Mount Whitney, minus our initial, which is Death Valley, right? And so that ends up being 2.93 times 10 to the 6th joules. Okay, so it's how much they gain. All right. Now, what is the kinetic energy of a 1,500-kilogram car traveling at a speed of 30 meters per second, which is approximately 65 meters? Then from what height would you have to drop the car to have the same amount of kinetic energy just before impact? Okay. And so if we just simply do our kinetic energy formula, 1/2 mv squared, we're going to get 1/2 times 1,500 times 30 squared. And so we'll have a kinetic energy of 6.75 times 10 to the 5th joules. right? So that's how much kinetic energy it has while traveling on the road. Now, how high will we have to drop it from? Well, then we use our potential energy formula, right? UG equals mgh. Solve this for h. So UG over mg. And so we want to have that equivalent or that same kinetic energy. So 6.75 times 10 to the fifth divided by 1500, right? The mass of the car, because that's what we're going to drop, times 10. And so we would have to drop it from a height of 45 meters. All right. Now, one thing we'll do is later we're going to learn an equation that calculates the gravitational force between any two objects, okay, when separated by centers. This is known as Newton's law of universal gravitation. The formula is F equals negative GM1 M2 over R squared. Last year you didn't put the negative sign, but just understand that this negative sign just simply indicates that gravity pulls objects. And if the sign were positive, it would indicate that gravity wants to push objects away. Okay, but we know that gravity pulls, right? And so here's an example talking about deriving an expression for a universal gravitational potential. And so we know that U is negative integral of F dr. Right, we're going to call it R because we're using R in our formula there. And so we're going to say negative G, or negative integral of GM1 M2 over R squared dr. And we can just, do some simplifying and pull out that GM1 M2, or that negative, right, which turns everything positive. Rewrite this negative R to the negative 2 just makes it a little bit easier to work with. And so this becomes, when I take the integral, GM1 M2, okay, times negative R to the negative 1. Remember, n plus 1 over n, it's raised to the n plus 1 over n plus 1, but if I rewrite that, okay, it's going to be U equals negative GM1 M2 over R. And so this is another way we can calculate potential energy. And understand, this is universal potential energy, universal gravitational potential energy. It's universal gravitational PE. Okay, that formula will appear on the formula sheet. And then we're going to talk about potential energy curves next, conservation of energy, and then finally power.